chapter 10 is hypothesis tests regarding a parameter. It is continuing on with the whole idea of inferential stuff, like what does it mean about the population. So chapter 9 is all about estimating, so we estimate with intervals. Chapter 10 is all about testing, so we're going to test with hypothesis tests. So I'm going to read this example because I think this is a good kind of version of why are we doing this, all right? So it says, suppose a school superintendent reads an article which states that the overall mean score for the SAT is 910. Furthermore, suppose that for a sample of students, the average of the SAT scores in the superintendent's school district is 960. Can the superintendent conclude that the students in his school district scored higher than average? At first glance, you might be inclined to say yes, since 960 is higher than 910. However, recall that the means of samples vary about the population mean when samples are selected. So the question arises, is there really a real difference in the means? Like, did he really score 50 points higher? Or is the difference simply due to sampling error, meaning you took a sample, you didn't ask everyone? In this chapter, we'll learn how to answer that question. So do you guys agree that 960 is higher than 910? Right? But it was just a sample. So what if he didn't do a good job sampling and he just asked all of his honor classes? Is that the true population score for his whole class or school? No. So what we're going to do, and I call it, I don't know, I know it's not very politically correct, but I call it calling BS on people. Like, people are going to make these claims and we're going to be able to say, nope, you don't have the authority to make that claim, or yes, you do. So this is where you're going to kind of see, hopefully you've been collecting data throughout the semester. If not, talk to me because I have a backup plan, because believe it or not, students forget to go collect data and I'm used to that. So I have a backup plan for you, so don't worry, you'll still be able to do the project, but you all made a claim in the beginning. So you said, I cuss 18 times a day. You're going to be able to test whether that's true or not now, all right? So 10-1 is no calculating, which might be good for you. So some people don't like numbers, so 10-1 is all about language and vocab. So let's see how far we can get. So 10-1 is the language of hypothesis testing. Objective 1 is to determine the null and alternative hypotheses. Right there, guys, those are kind of our first vocab words, all right? So how do we do hypothesis testing? Step number 1, a statement's made regarding the nature of the population. That's what you guys did. So you made a claim that I drink 100 ounces in a day, or I work out 60 minutes in a day. You made some kind of claim, right? Step 2, evidence, aka sample data, is collected. That's what you guys are supposed to have been doing all semester, is collecting your data, right? And step 3, you analyze the data to assess the plausibility of that initial statement. And that's what you'll do here in the next week or two, where I give you the project, you'll be able to say, oops, I'm a little bit off, or wow, I was really accurate, okay? So the first fill in the blank is hypothesis. Hypothesis. What is a hypothesis? It's a statement regarding a characteristic of one or more populations. Did anybody do science fair projects like when they're in junior high? The if-then statements, if I do this, like if I water my plant a lot, then it will grow, right? That's the hypothesis. You make this claim. The second one is hypothesis testing. So after the hypothesis is made, we're going to collect data, and we're going to be able to use that data to test, and that's called the hypothesis testing, okay? It's a procedure that you guys are going to learn in 10.2 and 10.3 based on the data you collected, so your sample data, and you're going to use it to test your claim of one or more populations. It says one or more, but guys, since you're in 145, you're only doing one population. If you're in 235, the upper level stats, you would look at more than one population, but we only have to worry about one, all right? So these are our new things that are going on. The first hypothesis is based on, it says, a statement can be either true or false. So hypothesis testing have a couple different hypotheses that can happen. The first one's called the null hypothesis, N-U-L-L. And it's the both fill in the blanks for that definition. All right. The most important part about, there's a lot that's important about the null hypothesis, but you want to make sure you know that you denote them with H sub 0, okay? H naught is how you say it. So the null hypothesis denoted H naught is the statement to be tested. So that's your claim. I work out 1 hour a day, okay? That's my null hypothesis. It's always assumed to be true until indicates otherwise. Have you heard the phrase innocent until proven guilty? like criminal justice kind of idea. It's the same idea. I work out an hour a day until you guys can prove that I don't, right? You stalk me and see, oh gosh, she doesn't even work out. So that's innocent until proven guilty. So it's true until you can prove otherwise. This chapter, it will be the statement regarding the value of the parameter. And notice it's a population parameter, so it'll be P, mu, sigma, any of those things that stand for population. All right, so here, the next one is alternative hypothesis. And again, it's both fill in the blanks. So go ahead and fill in both of those alternative hypotheses. What's it mean to be alternative? The root word is alternate, right? So if it's not the null, it's the alternate, right? Again, key thing is to remember that it's denoted H sub 1. H sub 1. So this is usually the person that's trying to call BS, okay? So you guys know I talk about all the time, I don't work out. So if I'm trying to claim that I work out for an hour, you guys would make the alternative hypothesis that I don't work out for an hour, okay? So the alternative hypothesis is Molly does not work out for an hour. It's the statement that it's kind of calling BS. Just kind of something like a little silly thing that people help them remember, they call it the ho and the high, because it almost looks like H-O and H-I, ho and high. It's the null and the alternative. All right, let's go ahead and flip it over to the top of page 2. At first, this looks really scary, but it's not, I promise, okay? You look at all these symbols and you're like, what the heck's going on here? All right. So, in this chapter, there's going to be 3 ways to set up our null and alternative hypotheses. So remember, H naught is your null. Please notice on every single one, H naught has the equal sign. Okay? So H naught always has equals. Okay? Because that is the claim. I work out an hour a day. I drink 100 ounces a day. Equal, equal, equal. Okay? How you can disprove that, how you can call BS on me, is in 3 ways. You can say, well, actually, I just don't think you work out 60 minutes at all. Okay? You don't say whether I work out more or less, you just say I don't work out that amount. So that's called a not equals test, and it's called two-tail, all right? Or you're like, you know what, I actually think you work out less than 60 minutes, so then it's a left-tailed test, and I don't think you'd call me out on this, but you can say, I actually think you work out more than 60 minutes, so it would be greater, okay? So H not always has the statement of equality, and whoever's calling you out is calling you out in one way or the other. Either it's not that, it's less than that, or it's more than that. So, how does that portray to you guys? Does anybody remember what they're collecting data on? Is anybody willing to share?
How many steps I take?
Okay. Do you remember roughly what your estimate was? Can I make it up? Okay.
How many miles I drive?
How many miles you drive? Do you remember what your estimate was?
100.
Oh, okay. A day? Okay, so hers says, I drive 100 miles a day. So every day she's been collecting data on this. And say she collects her sample data and the average is 45 miles. She most likely would do this one, that my average is less than 100 miles a day, right? Or Caitlin's, like say hers was like 5,000 steps and she actually walks 7,000 steps. She would actually try to prove that she walks more than what she originally said, okay? So let's look at these. It says an illustration of how a hypothesis should be stated. There's 3 different ways we can use it. 3 different symbols that we can use. We can use mu, p, or sigma, so depending on what we're talking about. So let's look at these 3 examples. A university researcher states that the mean number of years it takes a student to graduate with a bachelor's degree is not 4 years, okay? They want us to state the hypotheses. Every hypothesis test that you do in Chapter 10 is going to start with this. The null hypothesis, the alternative hypothesis, and the parameter, okay? The parameter is the symbol for whatever you're talking about. We're talking about the mean. What's the symbol for population mean? Mu. I heard it. Who said it? Who wins? I thought I heard someone say it. Maybe I just made it up. Someone said it. Okay, so we're going to have mu. All right? So, no matter what, if you're like, I don't know what's going on, at least start when it says state the hypotheses, label H naught and H1, your null and your alternative. Then go a step further and say, what are we trying to estimate? We're estimating the mean number of years. What's the symbol for population mean? Mu. What does the null always have? The equal sign, so this will always be equals. What does the alternative always have? What we're trying to disprove, right? And this one said is not 4 years. So what's the symbol for is not? That equal with the slash. Okay? So that means somewhere out there, someone tried to say you should get your bachelor's degree in 4 years, and someone's trying to say, you know what? I don't think it's 4 years. Did they say whether it was less or more? No, they just said, I don't think it's 4 years. And this would be a two-tailed test. Meaning, guys, and I know it doesn't make much sense now, but if it's not 4 years, we might look at something less or we might look at something more. We're going to look on both tails, okay? We're going to look at something less or something more. We're going to look at both tails. All right, let's look at example 2. It says a water faucet manufacturer announces that the mean flow rate of a certain type of faucet is less than 2.5 gallons per minute. State the hypotheses. So guess what you start with? H naught and H1. Choose your parameter. What's the symbol for mean? Mu. The null has always what symbol? Equals. And the alternative always has what you're trying to prove, and someone says it's less than. Is that okay so far? Less than what? 2.5 gallons per minute. So that means somewhere out there, someone at one point said it was 2.5 gallons per minute. And someone's like, nope, you know what? I think ours is better. I think we're very eco-friendly. It's actually less than 2.5 gallons per minute. So that would be considered a left-tailed test. So we would be looking at values to the left that are less than 2.5 gallons per minute. Are there any questions there why we use mu or why we use the less than symbol or why it's a left-tailed test? All right, last one. A department store claims that more than 5% of consumers purchase gifts for their fathers. So more than, but notice it didn't say mean anywhere. What did it give us? It gave us a percent. So guess what that is? P. That's our population proportion. So everything we test doesn't have to be about means. It can be about proportions. It can be about standard deviations, all right? So state our hypotheses. We'll have H naught and H1. What is our parameter for percents? P. The null always has a statement of equality. And then the alternative always has what you're trying to prove. What are you trying to prove? Greater than. And then change your percent, guys, to a decimal because that's how we're going to end up doing our calculations. So we might as well make our hypotheses have those decimal answers as well. And what kind of test will this be? Right tail. Are there any questions on those 3 examples? Go ahead and do A, B, and C without me. Go ahead and do A, B, and C without me, and I'll ask you guys what you got, okay? So now your turn. State the null and alternative hypothesis and which type of test it is, okay? So always write H naught H1. Feel free to talk to your neighbor or whatever, call me over. on these notes, I didn't ever use standard deviation, so you never use sigma, but on your homework you will. Like, just don't be scared by it. You can test over anything. You can test over the means, the proportions, the standard deviations. I think originally why I didn't use standard deviation in my notes is because we don't test over standard deviation. We're only going to be doing 10-2, which is proportions, and 10-3, which is means. But there's a 10-4 for standard deviations if you're in 235. So a couple of the 10.1 problems, you'll use sigma just to set up your null and alternative, but we won't see it past that, okay? So let's go ahead and look at what's going on here. On A, it said a recent magazine publicized that it takes the average woman more than 35 minutes to get ready in the morning. So you kind of see the word average there, and you see the word more than. So we're going to have H naught and H1, and we're talking about the average amount of time spent. So what's our parameter we're going to use? Mu. Null always has equals, and we're trying to prove more than, so we're going to have the greater than symbol. And then 35 minutes. Try to remember units whenever you're talking about your means. Is that okay? So you're trying to prove that the mean's greater than that, so he gets eaten, right? It's Pac-Man. The mean's bigger than 35, so that's the greater than symbol. B, a television manufacturer publishes that less than 72% of consumers own flat panel TVs. I need to update my notes here. You guys probably don't even know what a tube TV is. Does anybody know what a tube TV is? Where they actually had dimension to them. So anytime you're given a percent, your parameter is just P, all right? So this is H naught, P equals the 72%, and H1, P is less than the 72. And I forgot to write up here, guys, this is a right-tailed test, and this is a left-tailed test. And again, the whole idea why we're pointing that out is because we're going to look for extreme values, either greater in the right tail or fewer in the left tail. All right, the top of page 3, we have a consumer analyst reports that the mean life of a certain type of automobile battery is not 74 months. And again, mean is not. So the mean is mu, so we'll put mu. Is not is the not equals, and then 74 months is what they don't think it is, which means at some point somebody said it was. And since we don't say whether we think it's less or more, it's a two-tailed test. We got to look at both ends to see where things are. Anybody? 100%? Yeah. Not too bad? Well, did you see your error though? Like, was it the symbol going the wrong way? Did you shake your head no? Oh, okay.
That's not what happened. I misunderstood instructions.
Oh, okay. Do you see what we're doing now, though, Jake?
Yeah.
Okay. So the next thing is, once we set up our, so every hypothesis test that we do in 10-2 and 10-3 is going to be step number 1, state your hypotheses, okay? This is worth like 3 of the 10 points for a hypothesis test right here. Did you write the right parameter? Did you use the right symbol? And did you write the right tailed test, okay? So what we have to realize, though, is just like any court case, like if you're a lawyer or if you're a sergeant and you're trying to try someone on trial, they're either innocent or guilty, but they're either charged innocent or guilty, and you can make mistakes, and that's kind of how it is when we do hypothesis testing, okay? So objective 2 says, explain type 1 and type 2 errors. In a hypothesis testing situation, there are 4 possible outcomes. In reality, the null hypothesis may or may not be true, and you make a decision to either reject or not reject. So basically, you say guilty or not guilty, but that person's either innocent or guilty, okay? So what you want to do, leave room to write on top and leave room to write on side, but draw like a decent size square that we're going to cut into quarters. You guys ever do Punnett squares? In biology, you see what kind of colored-eyed kids you're going to have. That's kind of what we're going to do here, all right? So up top, we're going to have H naught true, or H1 is true, and this is reality. So either the null is true, I work out 60 minutes a day, or you guys were right, I work out less than 60 minutes a day, okay? So either the null, the left side, or the alternative, the right side's true. One or the other's true, okay? But you guys are going to make a decision, so that's called the conclusion. And you're either going to do not reject H naught, or you're going to reject H naught. And again, this is so foreign right now because we're going to talk all about hypothesis testing before we even do it, okay? So all these terms are like, why are we using the word reject? That kind of idea, okay? Reject is kind of like saying guilty, okay? So if we say guilty, that's rejecting. If we say not guilty, we're not rejecting. All right, 4 things can happen. 2 are the correct things, 2 are the wrong things. I'm going to try my darndest to make it make sense to you, but if not, that's okay. Just write them down, okay? So say my null hypothesis is true. I really do work out 60 minutes, and we did not reject it. We didn't get rid of it. Did we do the right or wrong thing? The right thing. It was true, and we didn't get rid of it. So that is a correct conclusion. And then I'm going to go to the next one, the next correct one. Say the alternative was true. I actually work out less than 60 minutes, and we rejected the claim that I worked out 60 minutes. Did we do the right thing? We did. So this bottom right-hand corner is a correct decision or correct conclusion. So if your null's true and you don't get rid of it, you made the right decision. If your alternative's true and you got rid of your null, that's still the right decision. You're just like, oh, guilty, you're going to jail, all right? But what can happen here is we can do 2 things wrong. Our null might be true. I don't work out 60 minutes a day, but you guys didn't get rid of that. That's called a type 2 error. Okay? And then the null could be true, like I really do work 60 minutes a day, and you guys got rid of that. That's called a type 1 error. They use Roman numerals there. There's a lot going on. So basically, like going back to the lawyer case, is this is an innocent person and we said not guilty. We did the right thing. An innocent person, we said not guilty. But what if the person was innocent and we said guilty? We did the wrong thing, right? We sent an innocent person to jail. So that's not good. So we're going to try to avoid type 1 errors. Then here, this is a guilty person, but we said not guilty. That guy's going hee and running out of the courtroom. I got away with it, right? So that's a type 2 error. We don't want to do that. But if the person's guilty and we said guilty and sent him to jail, we did the right decision. So type 1, type 2 errors, neither one is good, but who wants to make the decision which one's worse, which one's better? What do you think's worse, sending an innocent person to jail or letting a guilty person go free? You think letting a guilty person go free is worse?
No.
Innocent person jail. It's hard. You can't. It's a trick question, guys. There's no right answer. They're both awful, right? They're both awful, right? And so that's what we have to realize. We're going to get into like an ethical debate and stats here. That's what we have to realize. Neither one is a good thing, so we want to avoid both, okay? So let's use this Punnett square to help us fill in the blanks. I used object instead of reject. It's the same idea. What error was it when we rejected the null when it was actually true? We rejected the null when it was actually true. That's a type 1 error. Is that okay? That's a type 1 error. And then which one was it when we did not reject the null when it was false? That's a type 2 error. Okay? So this, guys, is just telling you if I don't make sense, the same kind of explanations given to you in your book, if anyone touches the book, it's in there, okay, about innocent person going free. So the last thing I want to fill in before we leave for today is the fill in the blank down here. It's called level of significance. Level of significance. This is what you want to kind of star or underline because it's something minor in the notes, and we honestly don't do a whole lot more with it in the notes. But your homework's good. Don't put things away yet, guys. We still got to fill this in the top of page 4, okay? It's something that's minor in the notes, and we don't do a whole lot with it in the notes, but my math lab will ask you about it. The level of significance is the probability of making a type 1 error, okay? And that's a key thing. We don't want to make a type 1 error, so do we want our probability to be high? No, okay? So sometimes they say, well, what is your level of significance? What does it mean? Just remember, it's the probability of making a type 1 error. And its symbol is alpha. Its symbol is alpha. And we were just arguing which one is worse, type 1 or type 2. Both are bad. Type 2 symbol is beta, and it's the probability of making a type 2 error, but it's too hard to calculate, so we're not going to calculate it. So guys, for purposes of this class, we're really focusing on type 1 errors, which are labeled alpha. So go ahead and flip it to the top of page 4. What are the most common values of alpha? Well, do we want to make a type 1 error? No, so we want them to be small. And guys, the alphas go hand in hand with the confidence levels in our chapter 9 notes. The most common levels are 0.10, 0.05, and 0.01. A tenth of a percent, or 10%, 5%, or 1% chance. Those are the most common, okay? And again, it's just the complement of the most common confidence levels, 90, 95, 99. Okay, so the question arises, and you guys don't ask this because you're like, I'm just taking stats because I have to, right? But if someone was a thinker and started thinking about it, why would we just not make it the lowest probability ever? Why wouldn't we always just make alpha 0.01? I want a 1% chance of making a type 1 error. Because once you lower that, what does that mean? It means you're really hesitant to say guilty. But if you're really hesitant to say guilty, what's going to happen? Guilty people are going to go free. So you're like, oh gosh, I don't want to put an innocent person in jail, so I'm not really sure if they're guilty. I don't want to say guilty. And that person walks out of the courtroom and he's like, I was guilty, you know. So when you lower alpha, you're raising beta. It's like a scale, okay? So let's write that down. So we want to keep it balanced, all right? By reducing alpha, the probability of making a type 1 error, you are increasing beta, and beta is just like a crazy B, which is the probability of making a type 2 error. By reducing alpha, you're increasing beta. So again, that's not a good thing either. So what we do is we kind of just stir the pot. Sometimes we'll do 0.01, sometimes we'll do 0.1, 0.05. Just that way, everything has the same kind of likelihood of occurring. Okay?